Hear me? Having trouble getting it close enough. Can you hear me? Great. Hello, I'm Rebekah Dawson, and I'm excited to talk to you today about some work from my thesis on constraining planetary migration mechanisms in systems of giant planets. So we think that giant planets form on circular coplanar orbits beyond the ice line. That's where there's enough icy, rocky materials to form a giant core, and as we heard about yesterday, undergo runaway accretion and end up as a giant planet. So these are the orbits that the planets form on, but somehow they go to this surprising diversity of orbits that we observe today. So here I'm plotting 1 minus eccentricity squared versus semi-major axis. And this is so that the more eccentric planets are at the bottom of the plot, and this scaling emphasizes the more eccentric planets. And you can see that there are planets with very large eccentricities. There are planets that are too close to their star to have formed there, and even hot Jupiters orbiting within 0.1 AU of their host star. As a side note, you might notice that most of the planets on these plots are a lot closer than the ones we heard about on Monday, and that's because we don't yet have a ton of well-characterized, widely separated planets. I sort of wanted to quote from Sean Andrews and say, there's a Jupiter mass planet at 20 AU. Don't ask me how it got there. It's not my problem. But actually, I think it is my problem. However, I think that a planet at 0.02 AU can tell us something about how a planet gets to 20 AU. And that's because the same processes that are operating in planetary systems to put planets on close-in orbits are operating in a wide range of systems of giant planets, including maybe some of them with more distant planets. And what we know about a planet at 0.02 AU is that it didn't form there, so then we don't have to disentangle the formation from the dynamical evolution. So here again, 1 minus eccentricity squared versus semi-major axis are the observed orbits of planets. And we want to know how we get from these orbits they form on to these strangely eccentric and close-in orbits. And there are two general classes of theory for doing that. I'm going to call them both planetary migration. One is gentle disk migration that we've heard a lot about in the past few days, where the disk that the planet forms in causes it to move in or out, and this is a fairly gentle process. The other type of process that I'm also calling migration are violent multi-body interactions among the planets that can scatter in a planet close to the star. And there's a few different types of mechanism for doing that I'm not going to go into. But in each case, there's strong gravitational interactions between the planets, and I'm going to call those violent multi-body interactions. So now I'm going to talk about what we expect these theories of planetary migration to produce in this eccentricity and semi-major axis parameter space. Smooth disk migration can move things around on circular orbits and account for the planets in the purple box. These multi-body interactions can excite the eccentricities of the giant planets. And some of them are on such eccentric orbits that they pass very close to the star and experience strong tidal dissipation, which can shrink and circularize their orbit. So if you have multi-body interactions followed by tidal circularization, you can populate the red region of the plot. So this is what we expect to see from these different mechanisms. And I want to point out that both smooth migration and strong multi-body interactions can lead to the hot Jupiters that are so strange and mysterious. So it's difficult to disentangle between these two processes just from the fact that we have hot Jupiters. So how can we start to do that? Here's again what we expect to see. So let's think about a planet that gets excited to a high eccentricity and then undergoes tidal circularization. It's going to move along this track of constant angular momentum, so one of these pink tracks, and end up as a hot Jupiter. So there's a recent prediction by Socrates and collaborators that use the number of Jupiters that are almost tidally circularized, so they have moved mostly along the track but still have some eccentricity, to predict how many super eccentric Jupiters there should be in this blue dashed region. And they predicted that in the Kepler sample, if this is the mechanism that's producing the hot Jupiters, this high eccentricity migration, that there should be 5 to 7 super eccentric migrating Jupiters in the Kepler sample. I showed that because someone told me that biologists were confused by the term migration because the planets don't come back. It's more like immigration. Okay, so we want to look in the Kepler sample for these super eccentric Jupiters, but the trouble is that traditionally, in order to get the eccentricity of a transiting planet like what the Kepler mission finds, you need to follow up with radial velocity measurements. And most of the Kepler stars are too faint to be well amenable to this and would take too much telescope time. So we developed an approach to measure the eccentricity of giant planets using the Kepler light curve. So we call this the photoeccentric effect, and it hinges on the fact that a planet transiting on an eccentric orbit is going to have a different duration and shape to its transit than one transiting on a circular orbit. And I don't have time to go into it, but for Jupiter-sized planets, we can overcome degeneracies between the stellar properties, the eccentricity, and the orientation of the ellipse. So ask me about that later if you're interested. So what type of population do we expect to observe in the Kepler samples if the hot Jupiters are being produced by these strong multi-body interactions instead of smooth disk migration? This is a plot of orbital period versus what I'm parameterizing as the transit speed relative to the speed the planet would have on a circular orbit. And this is a Monte Carlo simulation where the dark part of the plot are the planets that we expect to see. So we expect to mostly see long period planets that are transiting much more quickly than if they were on a circular orbit. And we expect to see about 5 of them in this dark region. So we went and measured the eccentricities of the Kepler giant planets from their transit light curves. And these are the measurements we found. So each bar represents our measurement, and they're thick because there's some uncertainty. But what we see is that not 5 super eccentric planets in this dark region. All the planets seem to have too low eccentricities to be moving along this tidal circularization track. So we didn't find the super eccentric planets that we expected if the hot Jupiters are coming from these multi-body interactions. But I wanted to highlight one particularly special planet, which is KOI 1474. 2 interesting things about it. One is that we measured an eccentricity of 0.8 from its transit light curve, which is rather eccentric, but it's actually a bit too far away from the star, its periapse, to be undergoing tidal circularization. So we call it a failed hot Jupiter. The other interesting thing is that this planet, instead of having periodic transits, arrives early and late in its transit. So it exhibits transit timing variations. And that tells us there's some other body in the system perturbing the planet. When we wrote this paper in 2012, we hadn't seen enough transits to pin down the identity of the perturber. But now we have a lot more transits, and we can start to do that and start to understand what's this other body that was responsible, perhaps, for giving the inner planet such a large eccentricity. So the exciting thing is that from just the transit light curves, we can get a 3-dimensional picture of the system. For the inner planet, we can constrain everything except its mass just from the transit light curves. And for the outer perturbing planet, we can constrain everything uniquely based on the transit timing variations that we see. And I'm going to preliminarily say, we're still refining this, that the planets are coplanar. So this would be quite interesting because one of the theories for putting planets onto an eccentric orbit is that you have one with a really large mutual inclination, and through what's called the Kozai mechanism, you can get a very eccentric planet, but that can't be what's going on in this system. The other interesting thing is that we followed up with radial velocity measurements. So these are taken by the California Planet team, and in black I'm plotting the model that I just took from my measurements of the transit light curve and my model of the transit timing variation and adjusted the mass of the inner planet. And you can see that it matches the data pretty well. So I think this is one of the first cases where we've detected a planet through transit timing variations and then followed it up through radial velocity measurements, and it's consistent with the transit timing variations. Okay, but overall, even though we found that one interesting guy, the expected super-eccentric progenitors are missing. So what is that telling us about giant planet migration? So we didn't find in the blue dashed region the super-eccentric progenitors that we expected. And that allows us to put an upper limit of 33% on what fraction of these moderately eccentric ones are coming in along these tidal circularization paths. This is taking into account the Poisson statistics. We might have just missed some and uncertainties in the transit light curves, but we know that we can't account for all of them. So that leads us to think what's happening. There could be, there could be multiple migration mechanisms, like maybe this super-eccentric migration is producing some of the hot Jupiters, but smooth migration is producing others, which would actually be a comforting explanation for why there's all these almost perfectly circular planets that are also too close in to have formed there. And so let me tell you something that's special about these moderately eccentric Jupiters that I have as blue stars that were used to predict how many super-eccentric Jupiters there could be. Most of them, here I'm just zooming in on the plot and 1 minus eccentricity squared versus semi-major axis, and you can see that most of these moderately eccentric ones I have as blue circles, whereas the hot Jupiters are a combination of blue circles and red squares. The difference between these is the host star metallicity. So the planets that are on, that are the moderately eccentric Jupiters moving along the track tend to be orbiting the most metal-rich stars. And this might be an explanation for why we might see different types of planetary migration. So if there's different types of planetary migration going on, it may be the properties of the protoplanetary disks that triggers which one is happening. So we've already known from studies, for example, by Fisher and Valenti, that giant planets are more common around the more metal-rich host stars, which is taken as evidence for core accretion. So if it's hard enough to form one planet around a metal-poor star, that's why it's square, because it's really hard to even form one circular planet. It's going to be really hard to form a bunch of planets around a metal-poor star. So maybe only around the metal-rich stars can you have a bunch of giant planets that would trigger these strong gravitational interactions. So we can have disk migration and strong gravitational interactions around the metal-rich stars, but around the metal-poor stars, mostly just disk migration. And now I'm going to quickly show you two other trends that are consistent with this possibility. One is that here's, again, the plot of 1 minus eccentricity squared versus semi-major axis. In the gray region, which is called the period valley because overall there's a deficit of planets there, you can see that the more eccentric planets that are near the bottom of the plot tend to be orbiting the more metal-rich stars, and those that are orbiting metal-poor stars are confined to low eccentricities. So the interpretation there is that it's hard to get a planet inside 1 AU. You need potentially many different planets to do that through multi-body interactions, or you can smoothly move it in through disk migration, but only around the more metal-rich stars will you have the large eccentricities that are a signature of the strong interactions. Then the last plot I want to show you is actually the second to last plot, is explaining an interesting discrepancy that's been found in the Kepler versus the radial velocity data. So it's been found that in the Kepler data, the occurrence rate of hot Jupiters is much lower than in the radial velocity sample. It's about a factor of 3. So here I'm plotting in red is the observed period distribution of the Kepler giant planets, and in black is the predicted distribution if it followed the same period distribution as the planets in the radial velocity survey. So you can see that based on the radial velocity surveys, we expect a pileup of transiting short giant period planets, but we don't see those in the Kepler sample. But we know that the Kepler sample, which is looking just above the galactic plane, overall has lower metallicities. So then as the last plot, I'm going to separate out the Kepler stars based on metallicity. So the top is the full sample, The middle panel is the more metal-rich Kepler stars, and the bottom panel is the more metal-poor Kepler stars. And you can see that we recover the pileup of short-period giant planets around the more metal-rich Kepler host stars. So the conclusion is that planets orbiting metal-rich stars show signatures of planet-planet interactions. So I had said there is two theories for giant planet migration that we're trying to distinguish between. And the answer that we're drawing from these studies is that maybe both of them are happening. And in fact, not just maybe, but that both need to be happening. At first, when I started this, I was suspicious. I thought that it's quite unlikely that you'd have two different mechanisms happening with the same amount of frequency. But actually, it's looking like we really do need two different mechanisms to explain the observed orbital distribution of the planets. And so I think what's next is to go back to this diagram and look in the region where of planets that aren't in any of these boxes. These eccentric planets that are in the period valley that aren't coming in through disk migration because they have such large eccentricities, but are too far away to also be tidally circularizing from beyond the ice line. People are working on this theoretically, including Christabel Petrovich in his thesis, and there's also a lot of observational work to take a look at these planets and see what are their spin orbital alignments, what other perturbers are in the system. But I think this is an interesting population to focus on because the migration theories have been fine-tuned to produce the hot Jupiters. And so these are a test case of another type of giant planet that the migration theories need to produce. So thank you very much.
Thank you, Becky. So we have time for questions.
Hi, so this might be a naive question, but aren't you getting a lower limit to the eccentricities from your transit durations? That is, you don't have to be transiting at periastron.
Great question. So we are absolutely getting a lower limit, but we're actually getting an even tighter constraint than a lower limit. So let me show you a plot really quickly that explains that. So here I'm plotting as a function of the orientation of the ellipse, the eccentricity of the planet, and this is a ratio of what can be thought of as a transit speed ratio. And what I want you to notice is that there's a minimum eccentricity, but also the minimum eccentricity curve is lying very tangent to this line. So when we marginalize over the orientations of the ellipse, it's actually very close to the minimum eccentricity. And I don't have a plot, but that's why we're getting more than a minimum. We're getting a pretty good constraint.
What are the current prospects for directly constraining this, kind of jumping migration scenario by just detecting the third body in a system?
Can you clarify the question? Sorry.
Well, what are the best prospects right now for constraining the presence of the third body in a system and systems where you need either quasi or scattering or anything like that?
So by third body, you mean the star, the planet you know about, and then the perturber?
Yeah.
Great question. So this is actually going to be really important for distinguishing which of these type of planet-planet interactions is going on. Because in something like planet-planet cosi, you need a fairly close-by perturber, is my understanding, and that's something that we'd be able to detect through transit timing variations or a radial velocity trend, like that example that I showed where we could detect the outer planet through the transit timing variations. But in something like planet-planet scattering, you might often eject the other planet, and then there's less evidence there. So I think we'll be able to say if it's planet-planet cosi. As far as some of the other mechanisms like scattering and secular chaos, it might be a little bit harder to disentangle, but definitely the identity or lack of perturbers is going to help us distinguish that.
We have 40 seconds for one more question.
There's also a metallicity eccentricity correlation at longer periods, though it's weaker only for higher eccentricities. Would this also, would this period dependence of that correlation say something about formation or scattering?
Yeah, I was focusing on where we see, I think the reason we see the trend most strongly inside the ice line is that if you have two planets, you can imagine even exciting high eccentricities, but it's pretty hard to drastically change the planet's energy so much so it moves from 0.1 AU to 0.3 AU. So I think in that case, you need 3 or more giant planets, and that's really demands possibly a high metallicity in the disk. But we may see some signatures at longer period, and I think if this is really what's going on, there's going to be other factors contributing too, like the mass of the host star. So we should be continuing to look at this, but I think the first order strongest effect that we're seeing now is shorter period inside the ice line metallicity correlations, yeah.